Welcome to the Water Environment Research Foundation's TERI tutorial series. This module will walk you through a case study for plant C. This plant has a total nitrogen limit of 5 milligrams per liter. Currently, the permit does not include a limit for total phosphorus, but the plant's average total phosphorus discharge is 0.5 milligrams per liter. There is no solids stabilization process at this facility. The plant receives mostly domestic waste. It is currently treating 5.3 million gallons of wastewater per day. The UCT biological reactors meet the plant's discharge permit limits of less than 5 milligrams per liter of total nitrogen. The plant has no phosphorus limit, but the average effluent total phosphorus is 0.5 milligrams per liter. Centrifuges are used to dewater the undigested sludge prior to landfill disposal. This is the overall plant schematic for Plant C. Some highlights of Plant C's process are as follows. Waste sludge is held in sludge holding tanks until it can be dewatered with centrifuges. The sludge cake is disposed at the local landfill. Centrate is returned to the head of the treatment facility. Plant personnel have been looking at alternatives for solids handling. They are interested in checking into the financial feasibility of using waste-activated sludge release to create an optimal waste stream to be used for nutrient recovery. Here is a summary of the influent, secondary effluent, and final effluent data that we have for the plant. There is no data for the side stream centrate flow. Some additional information that was entered for this case study includes the importance of each of the business case evaluation criteria, the average labor rate for operations and maintenance personnel at the plant, which is $20 per hour, the local cost for magnesium chloride and sodium hydroxide, and the biosolids disposal cost, which is $21 per dry ton. When you first open TERI, remember to click Enable Macros when prompted. This allows the tool to operate correctly. On the Start screen, the plant data is entered, starting at the top of the green column and working down through each green box. When the box that says Specify Solid Stabilization Process is answered as No Stabilization at Present from the drop-down menu, the red box labeled Click Here to Enter Data for Sludge Holding Facility will appear. Please note that if no solids stabilization is practiced at a facility, the TERI will assume that enhanced WAS release will be employed in order to support nutrient recovery. While entering data, please keep in mind that the Clear Data button should only be used when you want to erase all inputs in a tab. To change individual entries, just click on the cell and use the backspace button to delete that particular cell entry before entering the correct value. For plants that have no solid stabilization process, data will be entered on the Sludge Holding Facility screen, which is located at the Type 4 tab at the bottom of the screen. This is the screen that will pop up when you click on the red button labeled Click Here to Enter Sludge Holding Tank Data. The data entered here comes from the plant performance data table that we looked at earlier. Enter all of the data that you have available. Leave cells for the data that you do not have blank. The tool will assume some default values for critical data if nothing is entered in those fields. The business case evaluation criteria weighting is entered as shown here. These criteria weights will determine the formula used to calculate the BCE scores for each alternative. Please note that the 3 case studies shown in the TERI tutorials all use the same criteria. This helps to make it possible to compare the results and see how the different plant configurations affect the overall scores. The plant mass balance shows an approximation of the concentration of solids and nutrients at various points in the process. The The results for Plant C can be accessed by clicking on the Plant Mass Balance text at the top of the screen, or by clicking on the blue MB Schematic tab at the bottom of the screen. The mass balance produced by Terry simplifies the process somewhat to prevent the model from getting too complicated. Based on the data entered, Terry calculates these values for the mass balance before nutrient recovery for Plant C. This slide shows a close-up of several of the boxes where the most significant changes in the balance occur. Once all of the data is entered, the expected performance of several options and the capital and O&M estimate results can be viewed by clicking on the Capital and O&M estimate results at the top of the Terry screen, or by clicking on the blue tab labeled Results Struve at the bottom of the Terry screen. This is the screen with the results that will pop up. It presents a side-by-side comparison of the calculations for each of the following options: Struvite Crystallizer High Estimate, Struvite Crystallizer Low Estimate, Ferric Chloride Addition, and Alum Addition. The benchmark for the performance of these options is 85% removal of orthophosphorus from the side stream flow. Since there are 84 pounds per day of orthophosphorus in the side stream, 85% removal would result in 71 pounds per day of orthophosphorus being removed. This is a summary of the capital investment needed to install the system, the annual operations and maintenance costs to keep the system running, and the value of the struvite that is recovered for each of the 4 alternatives. The business case evaluation, also referred to as the BCE, in the Terry is intended to help utilities take a very high-level, conceptual look at struvite recovery for their facility. Capital and O&M cost estimates must be verified. Remember, all capital cost estimates are based on 2012 U.S. dollars. The BCE rank scores are based upon the weights that were entered for the 13 specific business case model criteria. There may be additional criteria that should be used to assess the options. Therefore, the Terry provides a good starting point for looking at nutrient recovery options, but additional study and evaluation is needed before any fully informed decisions can be made on implementation. Terry uses several parameters in the financial portions of the BCE. The nominal discount rate is the assumed interest rate without inflation being taken into account. Therefore, the real discount rate is the interest rate adjusted for inflation. The evaluation period that the tool looks at is 20 years. For Plant C, based upon the business case criteria weighting that was entered, the struvite recovery low estimate alternative has the best total score of 75.3. For comparison, the baseline scenario represents the condition where plant O&M staff take the necessary operational and/or maintenance steps to minimize the effects of nuisance struvite formation. This table shows how each of the BCE criteria areas contribute to the total score for each of the alternatives. This graph compares the net present costs of each of the 4 alternatives that are being evaluated. The lines for all 4 of the alternatives show significant increases in the net present cost each year because the systems have significant annual O&M costs. The struvite recovery options do take into account the value of the recovered struvite product. However, this value is not enough to offset the significant cost of the caustic that is required for these options. This last chart shows how the total scores of the alternatives for Plant C compare to one another based upon the breakdown of the BCE criteria into 4 major areas: wastewater treatment plant performance, environmental, health, social, economic, financial, and risk assessment. The struvite recovery options have significant environmental, health, social, and economic benefits over the ferric chloride or alum feed systems. The struvite recovery from side stream flow low estimate has the highest overall score out of the 4 options due to the fact that it is the only option that scores fairly well in all 4 of the major BCE criteria areas.